So this lesson is about differential equations, and we'll be doing differential equations for a few lessons here. So we're going to talk about what is a differential equation and what does it mean to solve a differential equation. And then we're going to look at a method of solving differential equations called Euler's method, which approximates the solutions to differential equations. So first of all, a differential equation is an equation that describes a function, but it uses derivatives to do that. For example, dy over dx equals x squared over y. Y is the function, y is a function of x, and this equation here describes something about the derivative of that function. Or another one is dy over dx equals 1/2 y cubed. Or this one actually has a second derivative in it. This is why I said uses derivatives, plural. D squared y over dx squared minus 2y dy dx minus 3y equals 0, etc. So these equations, these are each individually a differential equation, and they describe something about the function y. Now, a solution to a differential equation is a function that satisfies the differential equation. So, for example, if I give you the differential equation dy over dx equals y squared, that's a differential equation. It's an equation describing the function y using a derivative. Then my claim is that y equals -1 over x is a solution to this differential equation. What I mean by that, if I plugged in y equals -1 over x here and here, in other words, if I took its derivative first, figure out what that is, and then I plugged it in over here and then squared it, those should be the same. So if I take y equals -1 over x, it's really -x and -1. So dy dx, the derivative is negative times -1 of x and -2. Well, that's 1 over x squared. And when I look at the differential equation that I was given, dy dx equals y squared, the LHS, the left-hand side, was the dy dx. Well, I just discovered it's 1 over x squared. So the left-hand side is dy dx, or 1 over x squared. And the right-hand side is y squared. Well, y squared just means take this function and square it. So I'm squaring the -1 over x, and I get 1 over x squared. And if you look at those, the LHS 1 over x squared and the RHS 1 over x squared are the same. Therefore, this function, y equals -1 over x, is a solution to this differential equation. Now, there may be more than one solution to this differential equation, just like there may be more than one solution to an equation like an algebraic equation. But this particular function happens to be a solution to this differential equation. I also wanted to add real quick that diff-EQ, diff.eq, is the abbreviation for differential equation, that one over there. So here we want to verify that this function here is a solution to this differential equation. Well, first of all, I don't like y prime, although it is technically correct. I prefer this dy dx notation, so I'm going to say dy dx equals 2xy is really the differential equation. So I'm going to take this function and try to plug it in over here. Well, on the left-hand side, I need to find the dy dx. So LHS equals dy dx. Well, using this function, I'm going to find dy dx. So the derivative of e to the x squared, this is a chain rule problem. So the derivative of e to the x squared is e to the x squared, and then times the derivative of the box, which is 2x. Or in other words, you can call it 2x e to the x squared. And then the RHS for the differential equation was 2xy. And I'm now going to substitute the thing that I think is a solution, which is y equals e to the x squared, is going to be 2x times the e to the x squared. And if I compare this thing to this thing, they are the same. Therefore, LHS equals RHS. And y equals e to the x squared is a solution to y prime equals 2xy. So again, if I have a candidate solution, I literally plug it in to see what happens, which means I might have to take a derivative or do a substitution or whatever it might be. The point, though, is that a function here is a solution to the differential equation. All right, consider dy dx minus 3y equals 3, a differential equation. We want to show that y equals c e to the 3x minus 1 is a solution to the differential equation for any constant c. So again, I'm going to test this function by plugging it into the differential equation. In order to do that, I may want to know what dy dx is. So dy dx is, when I take the derivative of c e to the 3x, c is a coefficient, the derivative of e to the 3x is a chain rule, so it's e to the 3x times 3. So I'm going to get 3c e to the 3x. And of course, the derivative of -1 is going to be 0. So there's the dy dx. So the LHS of the differential equation, which is dy dx minus 3y, is going to be, well, this is the dy dx. So 3c e to the 3x minus 3y. So minus 3 times, well, this is my y. So c e to the 3x minus 1. And now it's a matter of simplifying this. So I end up with 3c e to the 3x minus 3c e to the 3x. And then minus 3 times minus 1 is plus 3. So that's equal to 3, which is equal to the right-hand side. And therefore, this is now a solution to the differential equation. So now we are asked to sketch the solution curves for these different values of c. So first I put my x and y axes down. And now I look at what would happen if c were equal to 0, and I would get y equals 0 minus 1. So y equals -1 is the solution when c equals 0. So again, this is a sketch, so I drew a horizontal line. I labeled the y-intercept -1, so it becomes y equals -1. But I also labeled the solution c equals 0, because it's supposed to match up with this. I don't need to know what the equation of that line is. I need to know that it is the line that matched up with c equals 0. Now when c equals 1, I'm going to get y equals 1 e to the 3x minus 1. So the graph got moved down 1, so this becomes the horizontal asymptote. Otherwise, e to the 3x is an exponential growth function, and when x equals 0, the y-intercept is going to be 1 minus 1, which is 0. Again, I'm using the c equals 1 possibility here. So this is my quick sketch when c equals 1. It goes through the origin. It has the horizontal asymptote over here and exponential growth over there. Let's do c equals 2 next. So when c equals 2, I get 2 e to the 3x minus 1. I still got moved down 1, but the y-intercept now, when I plug in 0, is 2 times 1 minus 1, so it's 2. So it's going to be above this c equals 1 graph. It's also going to have about the same shape because, again, it's exponential growth. So I graphed this exponential growth, and I marked the y-intercept as 1, or 0, 1. Now when I do c equals -1, that would be y equals negative e to the 3x minus 1. That's going to reflect across the x-axis, and then, of course, move down 1. So it's basically going to be this graph reflected across the fake x-axis, which is the y equals -1. And again, when I plugged in 0 for x, I had -1 e to the 0, so -1 minus 1, so the y-intercept is at -2. So this is the c equals -1 graph. And then when c equals -2, I get a reflection of this graph across the fake x-axis, so it should be down here. So now this is the graph when c equals -2. So now I've got 5 different solutions to the differential equation with different values of c, and I just used my knowledge of what kind of a graph this was and just plugged different values in to figure out what that was going to do. And of course I labeled them c equals 2, c equals 1, c equals 0, c equals -1, c equals -2 based on this information, not what the solution was going to end up being, although I did need to know what the solution was going to be in order to make it work. Now, there's a second part to this problem, so I'm going to copy the relevant information onto the next slide. So here's the relevant information. I have the original differential equation, and I have the solution that I found, which is technically called a family of solutions because different values of c give you different results, but all of the solutions that look like this do work in the differential equation. So the question is, find the particular solution which passes through 0, 2. Well, since we know this family of solutions works, I basically have to figure out, well, which of the functions that look like this would go through 0, 2. So literally I have to plug 0, 2 in and find out what c is. So I plug in 0 and 2, and I simplify e to the 0 as 1, and I solve for c. I get c equals 3. But the question wanted the particular solution that passed through 0, 2. So just saying c equals 3 is not good enough. It actually wanted the solution, not the value of c. So the solution has to look like this, but with a 3 in there. So there is my solution, the particular solution for this particular problem. Now the last part says find the equation of the tangent to this particular solution at 0, 2. Now, when we find the equation of a tangent line, you need to know the point, which we have, and conveniently it's the y-intercept, and then you need to know the slope of the tangent line, which we find by taking the derivative. Now, the hard way to do this problem is to take the derivative of this function and plug in x equals 0 and see what happens. The easy way to do this problem is to say, well, I have a differential equation that tells me about the derivative. I'm just going to plug points into that equation. So if this is the differential equation and I want to figure out what happens at 0, 2, we say dy dx evaluated at 0, 2 minus 3 times, well, y was 2 equals 3. And I can add 6 to both sides. So I end up with dy dx evaluated at 0, 2 is equal to 9. And so now we figured out what the slope of the line is supposed to be, and we also know what the y-intercept of the line is supposed to be. So the equation of the tangent line is y equals 9x plus 2. But my point I was trying to make here again is that I didn't actually need to take the derivative of this function because I already knew how the derivative was related to points on the curve. So I could literally just take the differential equation and plug points in, or the point in, and work out what the slope was going to be that way. Now be careful to say dy dx evaluated at 0, 2 because it is not dy dx everywhere. This equation tells me dy dx everywhere, but specifically at 0, 2, there is a number associated with it. If you don't say dy dx evaluated at 0, 2, you are saying that dy dx everywhere is equal to 9, which of course it isn't. So now we're going to talk about Euler's method of numerical integration. And yes, it's the same Euler who discovered the number e. The first thing I want to point out is the book's notation that they use is very confusing. It's actually rather standard notation, but at this stage, I think it's not worth trying to understand their notation. The principle of Euler's method is actually relatively straightforward. So I'm going to use some slightly different notation, basically using notation you already know rather than trying to teach you something new in terms of the notation. So ignore the book's notation. I think the procedure that I show you is relatively straightforward. So the basic idea is that you're trying to solve a differential equation. And I'm assuming here that the blue is the actual solution to the differential equation, but finding the solution to the differential equation for some reason is not easy to do. And so what we can do is we can approximate the solution to the differential equation by doing the following thing. So we start with a known value, for example, this point over here, which we usually label x0, y0, which is a point that you're given an initial value on your final solution. And then what you do is you find the slope of the tangent line by using the derivative, by using the differential equation at that point, and you draw that tangent line and you follow that tangent line knowing that it's going to be close to the actual solution, but not necessarily exactly, because the actual solution is probably curved and your tangent line, of course, is not. So you're going to follow it for a certain distance. Usually that distance is labeled delta x. It would be the distance from here to here, for example. Now that delta x distance is also sometimes called the step size of your Euler's method iteration that you're doing. So now what happens is you followed that tangent line for a while and you got to a new point, and now we call that point x1, y1. And now we look at the differential equation again and look for the tangent line from that point. And so we get another tangent line and we follow that for another delta x over here. And that takes us to a new point, x2, y2, and we find a tangent line there using the differential equation, and we draw a line, and we follow that line for another delta x, and then we get to x3, y3, and then we again use the differential equation to find the slope of a tangent line. We graph that tangent line and find the equation of the tangent line, follow that tangent line for another delta x, and we get to x4, y4, and so on. Now, the actual curve may look like this, and the approximation we're getting is not a perfect match, obviously, but it should mostly resemble the shape of that curve. And so this is our approximation that we're going to use. which again is called Euler's method. Now, it's similar to when we used rectangles to approximate the area under a curve, which ultimately became an integral. This sort of these tangent lines are similar to those rectangles where we just approximated, and the actual curve would be like the actual area. This is easier to understand by doing an example, so that's what we're going to do next. Consider the differential equation dy dx equal to e to the x plus 1 with y of 0 equals 1, and we're going to use Euler's method with a step side of 0.1 to approximate y of 0.5. So we start by listing out the original point, y of 0 equals 1, x0 equals 0, and y0 equals 1. Now what we're going to do is we're going to find an x1 and an x2 and an x3, etc. until we ultimately get to x something equals 0.5. Now since the step size is 0.1, the x values are going to increase by 0.1 every time. So ultimately I will have an x1 which is going to be at 0.1, and then an x2, which is going to be at 0.2, and an x3, which is at 0.3, and an x4, which is at 0.4, and finally an x5, which is at 0.5. And once I figure out what my y5 is, then that will be the y-coordinate of my approximation using Euler's method. So first thing I did was figure out all the x values by just increasing by that step size. So the first thing I do now to calculate is to use the 0, 1 or the x0, y0 value in that differential equation. So I evaluate dy dx at that point 0, 1, and I get this value, which is 2. So I know the slope of the line, of the tangent line, to that particular solution to the differential equation at 0, 1 is going to be 2. Now to get the y1 value, we're going to take the slope that we discovered over here, multiply it by the step size delta x, and add on the previous y coordinate. Now this is actually just the slope point version of the equation of a line. So if you had the slope of a line and one of the points on the line, let's say hk was the point and m was the slope, well that means you got to move right by h and up by k. So this would be the point slope equation of the line. So if I were to solve for y, I would end up with y equals slope times x minus h plus k. Now the k is the point, the y coordinate of the point that's going to move the graph up by whatever it might be, and the x minus h is the change in x. So the x minus h here is becoming the delta x, which took us from x0 equals 0 to x1 equals 0.1. That delta x, the slope is the value we found from the derivative, and the k was the old y coordinate. So this is just y equals slope times x minus h plus k. So when I plug in, the slope is 2, the delta x was the step size 0.1, and then 1 was the old y coordinate, so 2 times 0.1 plus 1 is 1.2. So we now know that the second point from Euler's method is x1 equals 0.1 and y1 equals 1.2. So to do the next value, I'm going to have to find the slope of the tangent line at the x equals 0.1, y equals 1.2 location. So dy dx evaluated at 0.1, 1.2, and I plug this point into the dy dx equation. So I end up with this, and I'm now going to give you a decimal. So this now is going to be the slope of the line that I'm going to follow in order to get to the next point on Euler's method. So to do that, I have y2 equals, I use the slope I found over here, times the step size, plus the y-coordinate from the most recent point, which was 1.2. So y2 equals 2.3 or whatever, times 0.1 plus 1.2. So we end up with y2 equals this decimal. So now I've got the x2, y2 value. So I plug the x2, y2 value into the derivative, into the differential equation, and so I end up with this value, In this particular differential equation, I only need the x, so the y doesn't actually matter, but you may have scenarios where the y matters as well. So I plug it in and I get a new slope, which is right here. So I take that slope, multiply by the step size, and add on the old y-coordinate, the previous y-coordinate, which was the 1.43 value. So slope times the delta x, the step size, plus the old y-coordinate. So when I do my calculation, I end up with y3 equals 1.652, etc. So now I've got the x3, y3 value. So again, I plug the x3 or the 0.3 and the y3 into the differential equation to work out the new slope. So here it is. I plugged it in. I got the new slope. And again, to get y4, I use the slope I just discovered times the step size, and then I add on the previous y-coordinate, which was this one. And again, when I plug that into my calculator, I get this value. And so I take the x4, y4 point, and I plug it into the differential equation. So dy dx evaluated at the x4, y4 point, and I get this value for the slope. And so I use the slope value times the delta x, or the step size, plus the previous y-coordinate. Now the x5 is 0.5, which is what I was trying to figure out. So the y5 value can now be rounded to my appropriate 3 sig figs. So finally, we can say that y of 0.5 is going to be approximately 2.14 based on Euler's method. Now, this approximately equal is not just about the rounding, but it's also about the fact that the method does not give you an exact answer. It just gives you an approximation. All right, here's another one. Suppose dy dx equals x plus y of 1 equals 2. Use 3 steps of Euler's method to approximate y of 1.6. So the first thing I notice is that we're doing 3 steps of Euler's method to get from x equals 1 to x equals 1.6. So 1.6 minus 1 divided by 3 means the step size has to be 0.2. So delta x is going to be 0.2. Then I can start with my x0, y0, which is my 1, 2, and then my x1 is going to be 1.2 because I have to add a step size of 0.2 to the x0, and then x2 is going to be 1.4, again adding the step size of 0.2, and x3 is going to be 1.6, and that's essentially what I'm looking for. So these are my x values for Euler's method. So I start by plugging in the 1, 2 into the differential equation. So dy dx evaluated at 1, 2 would be, well, x was 1 and y was 2, so add those two up and I get 3. So I now know that the slope of the tangent line at this original point 1, 2 is going to be 3. So what I do is I take that slope, I multiply it by the step size, the delta x, and I add on the old y-coordinate to get the new y-coordinate. So I've now discovered that the x1 is 1.2 and the y1 is 2.6. So I now need to figure out what the slope of the tangent line is going to be at 1.2, 2.6. And so I plug my 1.2 for x and my 2.6 for y into the dy dx equation, and I am going to end up with a slope of 3.8. So I find my y2 by using the slope 3.8 times the step size, which was 0.2, plus the previous y-coordinate, which was 2.6. And so when I calculate that, I get y2 equals 3.36. So now again, I need to use my x2, which is 1.4, and my y2, which is 3.36, and plug those into the differential equation to figure out what the slope is going to be at that particular point. So I plug in x equals 1.4 and y equals 3.36 in here, and I end up with a slope of 4.76. So now I go and I find the equation of that line to get the y3. I take the slope, 4.76, times the step size of 0.2, plus the previous y-coordinate, 3.36, and I end up with 4.312. Now the question says approximate y of 1.6. Well, this is going to be my approximation of y of 1.6. However, what I'm going to say is y of 1.6 is approximately equal to, and I'm going to write 4.31, but my approximately equal to is not just about the fact that I need to round it, but again, Euler's method gives you an approximation anyway, so I wouldn't want to say y of 1.6 is equal to 4.31 anyhow. We'd want to write the approximation just because we're using Euler's method. And that's the end of the lesson.